Good afternoon, everyone. I'm Melvin Ilang-Ilang. I'm from UP Los Baños, and I will be presenting our project entitled AIoT-Aided Farm Management for the Optimized Production of Selected High-Value Crop. Okay, and listed below are our team members. Quick background about the project. So the project was brought about by the Mekoteco Joint Research Program and the National Tsinghua University in Taiwan. So actually, NTHU were able to work on this project first, but they focused on the production of dragon fruit. So just a quick background, dragon fruit is, the cropping cycle of dragon fruit is limited only to once a year. But NTHU was able to produce or to make it into 2 cropping cycles per year in Taiwan. Okay. So AIoT, so basically it's a marriage of artificial intelligence and Internet of Things. And so we are all familiar with artificial intelligence already, and then Internet of Things, like the previous presented project, it's also considered as an example of Internet of Things, the wireless sensor networks. So the outline of my presentation, first, I'll be presenting the needs assessment for this project. Next would be the theoretical framework, system architecture, field experiments, and the evaluation. So prior to the implementation of the project, we conducted a needs assessment, and we found out that in the case of tomato production, losses due to farm management inefficiencies were one of the major problems observed in a prior needs assessment and technology intervention studies conducted. Okay? So why did we settle in the tomato production? It is because of the proximity of UP Los Baños to the tomato farms available nearby, especially in the towns of Liliu, Santa Cruz, and actually even in Batangas and Cavite. And also, since our funding agency is DOST Picard, they advised us to choose a high-value crop. So tomato actually is considered as a high-value crop. So for our theoretical framework, we started with initial field verification. So we conducted focus group discussions with different farm associations and farmers in the, actually in the whole region 4A. Next, we conducted we determined the design considerations, conducted laboratory testing, field deployment, data gathering, modification and calibration, and lastly, the evaluation. So for the system architecture, it can be outlined using this block diagram. So we have actually 4 main components for the whole system. We have sensor nodes. So the sensor nodes, or as we call it in our project, the sensor poles, are strategically placed on plots so that we can measure the different environmental parameters vital for the cultivation of tomato. And then these sensor nodes are connected wirelessly to a master node, which then instructs the actuator node on what to do with respect to fertigation. And then the master node also sends the measured parameters to an online dashboard, which can be accessed remotely using any device. For the sensor node, here are the key parameters that we measured. So these 4 parameters were based on the parameters vital for the growth of tomato. So we employed temperature sensor, relative humidity sensor, soil moisture sensor, and we built in an LDR module to measure the PPFD and light intensity that goes into the crop. Okay? And then the microcontroller unit that we used has an embedded LoRa module balik lang natin, yan, to communicate with the master node. So why did we choose LoRa module? From prior needs assessment, based on the terrain of the farms that we have visited, the most appropriate wireless communication protocol to use is the LoRa, or long-range module. Okay, for the actuator node, for this study, we focused on the water requirements depending on the growth cycle of the plant. So besides the water requirement, we also integrated the fertilization or the application of fertilizer in the crop. So again, the microcontroller used here has an embedded LoRa module so that it can communicate wirelessly with the master node. So for the master node, again, it has an embedded LoRa module. Besides that, we added also a Wi-Fi module so that it can upload data in real time to the online dashboard. Besides the data being sent to the online dashboard, we also added an SD card module so that the master node can save data locally. So if ever that we can't send the data to the dashboard, the data can still be recovered via the SD card connected to the microcontroller unit. So here is a snapshot of the dashboard that we used. So actually, we utilized ThingSpeak API so that after getting all the data required, we can immediately export the data to MATLAB. Just a quick background, this project is a phase 1 of a program that we are developing. So we are still in the process of the continuation of the project. Yeah, so here we can see the time series graph of the parameters measured based on the readings from the sensor nodes. And for the field experiments, this is the example of one of our implementations. We planted, or we utilized 6 plots for this experiment, and then per plot, there is a different treatment. So for example, for block 1, plot 1, the treatment used was automated fertilizer application and scheduled irrigation. And then for block 2, plot 1, automated fertilizer application, then reactive irrigation. So the plots here actually has different treatment for irrigation. So first is the manual irrigation, next is the reactive irrigation, and then scheduled irrigation. So what are the differences of the three? So for the manual irrigation, this served as our control setup. So the manual irrigation is based on the farmer's practice on when they apply water to the plants. And then for reactive irrigation, so the actuators deliver water based on the measured relative humidity and soil moisture sent by the sensor nodes. And for scheduled irrigation, we just added this one because the farmer that collaborated with us in this implementation said that for their farm, they don't actually use the manual irrigation method. Instead, they have a scheduled one. So they water the plants in the morning and the afternoon. So we also implemented that one. And then for the fertilizer application, so for the manual fertilizer application, this is the base from the farmer's practice again. And for the automated fertilizer application, this one is scheduled based on the plant requirements, depending on the growth stage of the tomato. And this is the actual test site. So the one on the left is the master node. So there is a graphical user interface wherein the farmer can view the real-time updates from the sensor nodes. And also, the farmer can turn on or off the irrigation and fertilizer application. So the irrigation method that we used here is drip irrigation. To have better control of the volume of water. And then, as you can see, I hope you can see the sensor poles. We have 2 sets of sensors here. One is located about 1 meter from the ground, and the one is located about 0.2 meters from the ground. So the reason for having 2 sets of sensors here is that so that we can address the different growth stages. Okay. So the one on 0.2 meters from the ground measures the parameters while the plant is still a seedling. And then the sensors located 1 meter above the ground addresses the issue when the crop is already at the fruiting stage. So for the evaluation, we performed hydraulic performance evaluation based on these 3 parameters. So coefficient of variation, coefficient of uniformity, and emission uniformity. So based on our results, we determined that for CV, we have an interpretation of excellent. And then for CU, we have very good performance. And for EU, we have good performance. So this is based on the implementation using drip irrigation. Also, we measured the yield from this setup, and then we found out that the scheduled irrigation setup has the highest yield. Okay, so for scheduled irrigation and manual fertilizer application, it has 8,950 kilograms, and then for scheduled irrigation and automated fertilizer application, it yielded 8,525 kilograms or grams. I might correct that one. We also performed statistical analysis. So it was found out that for scheduled and reactive irrigation, there is no significant difference between the yields of the two. And their yield is significantly different for the manual irrigation treatment. And then we also performed cost-benefit analysis. So based on these numbers, we determined that for, depending on the farm gate price, so we categorize it to low, medium, and high farm gate prices. So if the farm gate price is low, the return on investment would be 2.51 years. Okay? If you consider 1 cropping cycle per year. For medium farm gate price, the return on investment would be 1.79 years. And for high farm gate price, the return on investment would be 1.33 years. And then we measured, based on our experimentations, the usable life for the device that we have created is for 5 years. So if we can utilize the device for 5 years, we can expect that the investment made would be put into good use. So for future enhancements, we can incorporate machine learning for optimized decision making and utilize data for informed farm management practices. That's all. Thank you.
Thank you, Mr. Melvin. We still have time for some questions from the audience. Anyone? Okay. I do have a question for Sir Melvin. I'm not sure if I missed it, but how many plants were used during the testing, and how significant is the size of the test size to determine the accuracy of the results?
For the one presented here, we planted 4 plants per treatment. And actually, this was already computed by a statistician. This was recommended to us.
Thank you. Any more questions from the audience? None. Okay. Last question from me. Despite the efficiency of your method, what are the barriers that our farmers face to be able to adopt this technology?
Based from our FGDs conducted, their main concern is pilferage actually. When they learned the cost of this system, they fear that when they deploy it in their farms, that baka lang nakawin. So yun yung isang malaking concern nila. And of course, since yung mga nakausap namin ay hindi naman sila yung corporations talaga, so yung initial cost doon sa pag-adapt ng technology, yun yung isang malaking concern nila.
Okay. Thank you, Sir Melvin. Now we can proceed with the awarding of certificate. Okay. Certificate of Appreciation is presented to Sir Melvin Ilang-Ilang for sharing their invaluable insight and work on AIoT, aided farm management for the optimized production of selected high-value crop during the NECE Con 2024, given this 19th day of July 2024 at Novotel, Manila, Araneta City, Quezon City, Philippines, signed by Dr. Liu Anru Tria.